Thank you very much for inviting me to talk and for coming and attending this talk, which is, I think, midnight in Japan. So thank you very much for all coming. This is a joint project with Srinivas Harigapudi from the Technion and my colleague at Bar-Ilan University, Amnon Schreiber. So many real-life situations can be modeled as coordination games with multiple pure equilibria, and specific in this talk and in the paper, we focus on one-shot games with two players, two action coordination games, in which before the players talk, they can observe a few past actions of other players who played the same game. In addition to the pure coordinated equilibria, the games also have mixed equilibria with miscoordination. And the existing literature shows various results in various related setups that populations that play coordination games always converge to one of the pure coordinated equilibria. Casual observation and some empirical data that I will present at the end of the talk suggest that sometimes miscoordination can persist even in such situations. And what we show in this paper, in this theoretical paper, is that heterogeneous noise, situation in which some agents have accurate information about the aggregate behavior, while other agents have small noisy samples, in such situation, heterogeneous noise can induce stable miscoordination, a situation in which players will be stuck in a situation in which some players play A, some players play action B. In many cases, they play different actions and there is miscoordination, and this will be stable to perturbations. And this will be the case in which some agents, but not all of them, rely on anecdotal evidence on small noisy sample. This will be the situation that miscoordination is stable. So first, let me give a brief survey of the many existing results that showing that miscoordination is unstable in coordination game. So first, it is well known that the mixed equilibrium is not neutrally stable, while the pure equilibria in coordination games is strict equilibria are evolutionary stable. Crawford 89 showing that mixed equilibrium is generically unstable for various learning dynamics. Bill Sandholm in his book showing that the mixed equilibrium cannot be asymptotically stable under the replicator dynamics, which is a commonly used dynamics for any underlying game, not even only for coordination games. Some results showing convergence to the pure coordinated equilibria from almost all states. Kanevsky and Young showing this in a similar dynamics to our own, which will be based that each agent has a sample of the opponent population. They show that if agents have sufficiently large samples, they will always converge to the pure coordinated, to one of the pure equilibria. And Opry et al. Showing that if the dynamic is payoff monotone, in the sense that an action that yields a higher payoff, its frequency increases, then again, there will be convergence always to one of the pure equilibria. And some additional results showing global convergence specifically to the risk-dominant pure equilibrium, to the action which is the best reply to the opponent playing each action with equal probabilities. Oyama et al. Showing it in situation in which most agents have small samples. And there is the literature on the stochastic stability showing that if there are large samples and players rarely do mistakes, then we also converge to this equilibrium. So there are many related setups, some with large samples, some with small samples. In all of them, there is convergence to the pure equilibrium. And what we will show in this paper, in our setup, the dynamics would be that each player observes random k opponent's action and then best reply to their sample. importantly, different agents might have different Ks, different sample sizes. And we will show 3 results. The first is that an heterogeneous population in which some, but not all of the agents have sample size 1. So some agents are very naive in the sense that they choose their action based on observing only one opponent action. So in such population, they can induce globally stable miscoordination. From any initial state, the populations would converge to an interior state with miscoordination. The second result will show that heterogeneity is necessary for stability of miscoordination, in the sense that if the population is homogeneous, everyone have the same sample size, then regardless of this sample size is small or large, any sample size, if everyone have the same sample size, it will always converge to the pure, to one of the pure equilibria. And our final result will show that heterogeneous population in which some, but not all of the agents have relatively small samples, but it's not important for the third result that the sample size will be 1. It can also hold if they have sample size 5 or 10. So if some of them have relatively small samples and others have very large samples, this can induce miscoordination, which is locally stable. Not globally, you will not converge to it from any initial state, but if you start sufficiently close to it, you will remain in this state. Are there any questions on the broad motivations or the brief summary before I will start presenting the details of the model?
Okay, so the difference between 1 and 3 is that you're jumping from a sample size of 1 to perhaps 2 or 3, right?
So it can be actually any. So you can have any K, 10, 20, 30, any K that you want, let's say 20. If some agent have sample size 20 and the other a very large sample,
okay, yeah.
Provided that one of the action is a sufficiently Q dominant for one of the population, so one of the actions is sufficiently risk dominant in the sense that I will define later, this becomes more and more difficult to satisfy the larger the K, then there will be locally stable miscoordination. So one requires very hard condition. It requires that specifically those with low sample sizes must have sample size 1, and then it gives a very strong stability condition. While in 3, we have a substantially mild, weaker requirement. We only require it can hold for any K, but the larger the K, the more difficult the condition for the payoff matrix.
Thank you.
But then the stability is somewhat weaker. It's only local stability, only asymptotic stability. Any other questions? Okay, so this will be the coordination game that we study in the paper. There are 2 actions, 2 different populations, 2 different players. Each of them has action AI and BI. If both players play A, they get high payoff, U1 and U2. If both play B, they get a high payoff that we normalize to be 1, the payoff for coordination on B. And if they choose different actions, each player gets low payoff that we normalize to 0. We further assume, and it will be without loss of generality, that U1 is larger than 1. So that A is the risk dominant action for player 1. And U2 is something positive. I will claim later that this, despite the fact that it has only 2 parameters, it actually captures any 2-action coordination game. I will explain it later. So in this game, there are 3 Nash equilibria. There are 2 pure coordinated equilibria, A and B. And in addition, there is a mixed equilibrium in which players play with positive probability each action. And this is inefficient in the sense that they are often play one of the miscoordinated outcomes of one player playing B and the other playing A. and in the sense that the payoff is lower for the mixed equilibrium. And now I would like to explain why this representation, despite having only two parameters, captures any game with two strict equilibria, any coordination game. So here in the left side, there is a general representation of a coordination game. So there are 4 different parameters for each player. And I assume that there are 2 strict equilibria. So specifically here, I assume that one equilibrium is both players playing A and one both playing B. The assumption that the equilibria are on the main diagonal, this is without loss of generality. If originally the pure equilibria were off diagonal, like in the hawk-dove game, I could relabel the actions of one of the players, and then the equilibria will move from the off diagonal to the main diagonal if I switch the actions of one of the players. So the assumption that the 2 strict equilibria are on the main diagonal, this is without loss of generality. And now the sampling dynamics that I will present a bit later, the agent best reply to a finite sample, depend only on the differences of payoff given the opponent action. So it only depends on the differences between U21 and U11 and the differences between U22 and U12. But that's it. It only depends on the differences of payoff because you consider which action to play. It doesn't depend on the absolute value of the payoff, only on the differences. And I just consider whether I should play A or B. And it only depends what is the payoff difference given some belief about the opponent population. And this is not only a property of our own sampling dynamics, this also holds for best reply dynamics, logic dynamics, many other learning dynamics, and also the set of Nash equilibria and the set of evolutionary stable state, all of them only depend on the differences of payoff. An exception for this, like a dynamic that also depends on the payoff themselves, not only on differences of payoff, is, for example, first, if there are dynamics that also learns on the payoff of, that also depends on the payoff of other players, some social preferences, then this wouldn't be the case. Or also the best experience payoff dynamics. If a player is unaware of the payoff matrix and he samples its action a few times and then choose the one that gives the higher payoff, but there are independent samples for its action, then this also would be an exception. But most learning dynamics, including the one that you use, only depends on the differences of payoff. And this allows us to do various linear transformation to the payoff. So if we start here in the original representation with 8 parameters, we can first subtract U21 from the payoff of player 1 in our first column. So now in the right-hand side, this is a similar matrix, except that if the opponent play A2 in the right matrix, then the player get U21 less utility points. But this also only depends on the opponent. It doesn't depend on the player's action. Therefore, it doesn't change the differences of payoff, and it doesn't change the decision of a player whether to play A1 or B1. Similarly, we can subtract U12 from the payoff of the player 1 if the opponent play her second action. And finally, we can divide all the payoff by U22 minus U12, and we get this a matrix that only has, we can call this ratio U1. For the other player, we can call this ratio U2, and we get the payoff with only 2 parameters. It might be that originally this number was less than 1. I previously mentioned that we wanted to normalize it to be always at least 1. But in this case, we can relabel the actions for both players and renormalize the payoff so that we get that what we call action A is the one that gives the risk-dominant equilibrium for player 1. Are there any questions at this stage about the payoff matrix or the normalization? Okay, so let me continue. Let me give an example how the hawk-dove game, what will be its standard representation. The hawk-dove game will be also the game that will be most closely related to the empirical application that I will present at the end of the presentation. So in this game, each player can be, it's a bargaining, think about a bargaining over a house, and each player can be a hawk in the sense of insisting on a favorable price, or a dove in the sense of willing to accept a less favorable price in order to maximize the probability of the bargaining succeeding and the house being sold. And there are, if both players are hawk, the bargaining is likely to fail. Each will insist on a favorable price. They wouldn't agree on a price. They will get a low payoff, which is normalized to 0. If both of them are dove, they will succeed. They will equally divide the surplus of trade. They will get a high payoff that we normalize to 1. And if one player is a hawk and the opponent is dove, the bargaining will succeed. The house will be sold, and the price will be more favorable to the hawk player. And we can normalize this as I did before and get a standard presentation where the parameter of player 1 is y minus L over G, and the parameter for the other player is G over minus 1. As part of this normalization, I relabel the actions of player 1 so that the pure equilibria will be on the main diagonal. Any questions?
Maybe a quick one. Oh, sorry, Alexander.
So yeah, I was thinking that here it is important that you're using like players have roles, right? So the role player and the column player are different. So you're not going to use one population dynamics, I suppose.
Exactly, it will be 2 population dynamic. If originally the outcomes were on the main diagonal, then it actually doesn't matter. The stability would be the same. But if originally, as in this example, the equilibria were off diagonal, then it will be really important because it's a coordination game only if you look at it as 2 different populations. So the formal model is 2 populations. The results can also be applied to a 1 population model, but only if originally the equilibria were on the main diagonal. Any other questions? Okay, and the last definition that we will need will be of risk dominance and Q dominance. So let me define it. So following Morris et al., an action is Q dominant for player I if it is a strict best reply to any mixed action of the opponent that assigns a mass of at least Q is some number between 0 and 1, to the counterpart action of the opponent. So let's see some example. 1 dominant is just being a symmetric strict equilibrium. 1 dominant means if I'm sure that the opponent plays the same action, that this is my unique best reply. 0 dominant is being a dominant action. 0 dominant means that anything that the opponent plays, my unique best reply is to play action CI. And in general, the lower the Q, the more demanding the requirement. For 1 dominant, it is the weaker requirement, only requirement being a strict equilibrium. It becomes more and more demanding, and for Q equals 0, it requires it to be a strictly dominant action. The more well-known notion of risk dominant action is the case when Q is equal to half. It means that this action is the unique best reply whenever the opponent either plays uniformly or assigns higher probability for this action. And we call the action profile, we call it a risk dominant equilibrium if it is risk dominant action for both players. Because we allow the player to be asymmetric, it might be that action A is risk dominant for 1 population and action B might be risk dominant for the other populations, or it might be that they have the same risk dominant action. So in our parameterization, action AI is risk dominant if and only if UI is larger than 1, And action BI is risk dominant if and only if UI is smaller than 1. This determines the risk dominance in our setup. And observe that Q dominance depends only on differences in payoff, and therefore the various linear transformation that we do not affect the Q dominance. Q dominance is the same in the original game as the same after the linear transformation that we do to have only 2 parameters. By contrast, this is not true for payoff dominance. So I will not say anything about what is payoff dominance, because payoff dominance changes when we do the linear transformation, but risk dominance do not change. Any other questions? Okay, so let me present the dynamics, formally present the dynamics that we apply in the paper. So we think of a unit mass continuum of agents in each population, 2 different populations. A state of the population is some number in the unit square, P of t, where the first number, or Pi of t, describe the share of agents playing the first action, action A, at time t in population I. Formally, it's like a mixed action profile. Population state is like a mixed action profile, is some distribution of action in each population. And we think of a population interpretation that each player plays a pure action. And when we see something mixed, it's like heterogeneity in the population level, that some players play action A and other players play action B. So for example, 0-0 is the state in which everyone plays action B. And half-half is a situation in which in both populations, half of the players play A and half of the players play B. We assume that agents die at a constant rate. Regardless of what they play, there is a constant rate in which agents die or retire and get out of the population. We normalize this constant rate to be 1. These new agents are replaced by new agents. And the new agents, how they play is determined by some exogenous function W that captures the learning process. I will describe W in the, I think in the next slide. W will capture the sampling, the idea that you sample and best apply to the sample. So the state evolves according to the following differential equation. The derivative of the state is the inflow minus the outflow. The outflow is just proportional to is just P of t because there is a constant death rate. And the inflow is Wi of P of t. It's the share of the new agents that learn to play action A. And this determines how the frequency of players that play action A, how it increases. So the only thing that remains is to describe what W is. Given a function for W, this will complete the description of the dynamics. Are there any questions at this stage?
Maybe quickly. So W, so you may seem to know what's going on at the moment. Because
not necessarily. W depends on P, but W might be something very simple. For example, W might be constant. So W only depends on the current state. So there is no memory of the past, but perhaps the dependency might be very simple so that you use very little information about the current state. And our goal would be to characterize the limit points of the dynamics, which states are the limit of P of t for all initial state. And the interpretation of these limits will be prediction for long-run behavior. Something similar, if the dynamics was payoff monotone, we know that this limit would be a subset of the Nash equilibrium. The dynamics that I will present sometimes will violate payoff monotonicity, and therefore the stable state will not necessarily be a Nash equilibrium.
Can I ask just one question? So why do you select to I mean, the motivation is that people are sampling, but that sounds like a discrete process to me. Why do you choose to have continuous time?
So I think of situation that each player only samples one. Either each player only plays once, or if he plays more, he has no more further learning opportunities. Perhaps at a young age, you learn what to do, but then you become inflexible. It's very costly to change it. So players only play once. So now I think the result would be the same whether time is discrete, and then each player, a few of the agents change the behavior, or continue, and then it is a bit more tractable to do it in continuous time. But the important assumption, I don't allow players to continue learn throughout their lives and to accumulate a lot of experience. You only learn in the beginning. Okay. Okay. So let me briefly repeat the standard definitions of dynamic stability that we use in the paper.
Sorry, Robert. So the sampling will be in the W function, Robert?
Yes, exactly. The sampling will be captured in W. Our new agents decide what to do. Once they decide what to do, they play the same until they die, or they only play once.
Okay, sorry.
Okay, so a state is stationary if whenever you start with P, you remain in P. This will happen if W of P, the way that new agents behave, is the same as the way as the old agents behave. So if W is a fixed point of, if P is a fixed point of W. A state is a Lyapunov of stable. This would be the weaker notions of stability that we have in the paper. If any nearby population remain closed. So if we start nearby P, we always remain nearby P. We never go away, but we don't necessarily converge to P. The slightly stronger stability requirement would be asymptotic stability. This requires that if you start near P, not only you never go away, but also eventually in the long run, you converge to P. And the state is unstable if it doesn't satisfy the slightly weaker notion of stability. Any questions? Okay, so now let's describe W and the sampling process. So each population has some exogenous distribution, theta I, of sample sizes in the population. Theta I of K is the share of new agents in population I that have sample size K. If everyone in population I has the same sample size, I will just write as theta Y equivalent to K. But potentially theta I might assign masses to different K. Perhaps some agents have sample size 1, other agents have sample size 5, other have sample size 1000. So a full description of the environment in our setup will have two components, the payoff matrix, which is captured by two numbers, U1 and U2, and the distribution of sample sizes in each population, theta 1 and theta 2. There is only one mild assumption we take throughout the paper. We assume that in each population, some agent have sample size of at least 2. The situation in which everyone has sample size 1 gives we know what it gives. If everyone has sample size 1 in both populations, then the entire diagonal is Lyapunov stable, and the dynamics looks like this. From any initial points, you go in a 45 degrees line, converge to the some point in the main diagonal. This implies that if everyone has sample size 1, we always convert to a situation in which in both populations, the same share of agents play action A, but we don't know what this share will be. Perhaps 10% in each population will play A, or perhaps 90% in each population will play A. We do not know what it will be. As soon as we assume that in both populations there are at least some agent with sample size 2 or more, then this will not be the case. There will be a finite number of stable state, and we could have like a strong prediction that the population would converge to a small number of stable state and not to a continuum like this.
Can I ask one thing?
Yes, please do.
What are they sampling here? In the
So I will describe it in the next slide. They sample actions of the opponent population. They have IID observations of the distribution of the other population. I will describe it in more details. So perhaps if the other population, 60% play A and 40% play B, and my sample size is of size 3, then each of the action that I observe with 60% is A, with 40% is B. And the number of observation of A would be like a random variable with a binomial distribution.
Uh-huh.
And then we give more details in the next slide.
Okay, thank you.
And what
Another implicit assumption that I do is that any agent sample at least one action. So I don't allow actions that don't observe anything and just play something which is completely noisy. Okay, so now let's finish the description of the dynamics of what they sample, and we apply an existing dynamics originally presented by Bill in his paper from 2001, later on independently presented by Osborne and Rubinstein in 2003, and the heterogeneous version with different sample size was developed in Oyama et al. Paper. So each new agent with sample size k, I will sometimes call it a k agent, samples k randomly drawn opponent section, independent draws, and plays the action that is best applied against the sample. So sometimes there might be a tie, perhaps I sample perhaps some sample in which both of my actions give the same payoff. In this case, we will use some arbitrary tie-breaking rule. We use for tractability a tie-breaking rule which is in favor of the first action in case of a tie, we play A. But the result, all of them are essentially the same for any tie-breaking rule that you play. Tie are very rare. It's only open with 0 probability, the ties between A and B. So the number of A's in the sample as a binomial distribution. We write this random binomial variable as xk of pj. It's like a binomial variable. You have k trials, your sample size, and each trial has probability of pj to succeed to be action A. So the total number of A as a binomial distribution. So what would be the sum of payoffs of playing A against the sample? Each time you play action A, you get UI if the opponent plays A, you get 0 if the opponent plays B. So this would be UI times X, UI times the number of AI in the sample. Similarly, the sum of payoff of BI against the sample will be just the sum of BI, because the outcome B gives you payoff that we normalize to 1. So this will be K minus X. So AI is the best applied to the sample only if the binomial variable X is larger than K minus X. If if U times X is larger than K minus X. And we can, this is for an agent with sample size K. And now for the population, for the heterogeneous population, we do the mixed average of this, where the weights are the mass of each sample size. And what we get that a W is this mixed average of a CDF of binomial distributions. And this gives us an explicit formula to WI. And what is interesting that this is a polynomial and the degree is that the maximal sample size in the population. Matthias, do you have a question?
Yes, I do. So when you say the ties happen with probability 0, I can imagine that generically to be true, but if I take a specific game where the on-diagonal non-1 payoff is like 2, and I have a substantial share of individuals that have a sample size of 3, then it's not going to be a 0 probability event that someone has a tie, right?
Yes, you are absolutely correct. This is a 0 probability event only if I assume that the parameters are randomly drawn for some atomic distribution for specific value. It does happen, ties do happen with substantial probability. And then in this case, our quantitative result will depend on this tie breaking. Perhaps this will be convergence to equilibrium A and not convergence to equilibrium B because of this choice. But the qualitative results, the fact that whether there is or there is not stable miscoordination, this will be independent of the choice.
Okay.
Thank you. Any other questions? Okay, yes, okay. So the first result is to show global convergence to miscoordination if some, but not all of the players have sample size 1. So specifically, our first theorem shows that almost all states converge to miscoordination if the following 3 conditions are satisfied. First, it's required that each population would have a different risk-dominant action. If both players have the same risk-dominant action, so the game admits a risk-dominant equilibrium, this is always locally stable, so we cannot have global stability to miscoordination. So the first requirement is that the population would have different risk-dominant actions. In our parameterization, it will imply that U2 is less than 1, while U1 is more than 1. The second requirement is that the product of the share of agents with sample size 1 in one population times the expected sample size in the other population will be larger than 1. So in order for stability, in order for miscoordination to be globally stable, we need both substantial number of agents with sample size 1, but we also need that the expected number of observed sample to be sufficiently large, such that this product is more than 1. And finally, the third requirement is that U1 and U2 need to be sufficiently far from 1. This would be equivalent to requiring that the risk-dominant actions in each population is Q dominant for a sufficiently small Q. So I need them sufficiently far from 1. In the paper, we have an explicit characterization of this, how much U1 and U2 need to be far from 1. And this depends on the sample size. The larger sample sizes require U1 and U2 to be farther away from 1, while smaller sample sizes allow them to be relatively close to 1. So these are the 3 requirements that we need: different risk-dominant action, the product of this product larger than 1, and the UI sufficiently far from 1. Let me show in 2 examples. So in both examples, we look at a game in which U1 is 5 and U2 is 0.2. So action 1 is strongly risk-dominant for population 1, while action B is strongly risk-dominant for population 2. And in both examples, we assume that half of the population have sample size 1. In the left side, we assume that the other half of the population have sample size 2. In this case, the expected sample size is quite small, is only 1.5, because the samples are small. And because the expected sample size is quite small, this product is quite small, it is less than 1. And the condition is not satisfied, and miscoordination is unstable. So from any initial state, so in these squares, the x-axis is the share of agents playing action A in population Y, the y-axis is the share of actions playing population B, and we see the phase plots. From any initial states, we converge close to one of the curves. These are the curves of P1 equal to W1 of P2, where W1 is the learning rule, or P2 equal to W2 of P1. We converge to one of the curves, but then where we are in the area between the curves, we will move either to this pure equilibrium or to that pure equilibrium, and the stationary interior state is unstable. Any small perturbation will take us to one of the equilibria. In the right side, we can see the opposite case. We change the sample size of the other half of the population to make it 5. Now the expected sample size is sufficiently large. It is equal to 3, the average of 1 and 5. The product is more than 1. I choose originally U1 and U2 to be sufficiently far from 1 with respect to sample size 5. And as a result, we get global stability to the interior stationary state. The populations first converge to the area between the two curves, And then when they are in the area between the two curves, they always converge to the interior state with miscoordination. If there are no questions on the conditions of the theorem, let me briefly present the intuition, the sketch of proof. So first, the first observation is the risk-dominant equilibrium is always asymptotically stable. So this is why we need the UI to be in the different sides of one, to have the population to have different risk-dominant action. And now let's consider some state epsilon1, epsilon2, which is near B, a state in which very few agents play A in both population and almost everyone play B in both population. And let's assume that BI is risk dominant, but only with respect to population 1. So B is risk dominant for population 1, but A is risk dominant for population 2. And now I want to see whether from this state we will converge back to B or we will move away from B. This will determine whether B is stable or not. So the first thing to observe is that the probability of observing more than one action A in the sample is negligible. Because only epsilon of the other population play A, the probability that I will observe A twice in my sample is only O of epsilon squared. This will be negligible and we could ignore it. And now, we can only focus on which you observe sample A only once in the sample. And now let's first look at population 1. Population 1 is the one in which action B is risk dominant.
Can I ask a question in the meantime?
Yes, please ask.
At point 1, you say the risk dominant equilibrium is always asymptotically stable. So I'm a little bit confused because I thought what was risk dominant for the one was now not risk dominant for the other, right?
Yes, if I say risk dominant equilibrium, I mean that it is a risk dominant action for both players. So if both UI are larger than 1, then we cannot have global stability to miscoordination because the state in which both play A is always asymptotically stable. So if there exists the risk dominant equilibrium, if both UI the same side of 1, then we will never have global stability to miscoordination. So this can only happen if they are in different sides of 1, and then we don't have a risk dominant equilibrium. So now we are starting from epsilon. So let's look first at population 1. Population 1 is the one for which B is risk dominant. Because B is risk dominant and you only observe A only once in the sample, the only way that you can decide to play A, that A will be the best supply of the sample, is if your sample size is 1 and you only observe A. If your sample size is at least 2, you observe B at least 1 time, and because B is risk dominant, if you observe B weakly more than A, you will always play B. So the only way that you can, based on observation of a single A, play A is if your sample size is 1, the probability of this is theta of 1, and you observe A. The probability of observing A of the sample is epsilon 2, the share of actions, the share of the opponent population that plays A. So this will be the share of agents in population 1 that will play A. In population 2, it is different. In population 2, action A is the risk dominant, and therefore, for any sample size, a single observation of A might induce you to play action A, provided that action A is sufficiently Q dominant, provided that U2 is sufficiently small, sufficiently far from 1. So if U2 is sufficiently far from 1, a single observation of A will make you play A. What is the probability of observing A at least once in your sample? This depends on the sample size. It is approximately K times epsilon. Each observation has probability epsilon to be equal to A, and the total probability of observing at least A at least once, as long as epsilon is very small, is approximately K epsilon. So if I would do the average on the different K, I will get that this will be the expected sample size time epsilon 1. And now, if I look at the product of frequencies of new agents playing A in the two populations, this would be the product of these two terms, and I change the orders, I see that this is the product of agents, of incumbents, of all agents who played the rare actions, and this is multiplied by this product. So if this product is larger than 1, any small perturbations will become larger and larger with time, and if this product is smaller than 1, any small perturbation would die out. So this is the basic intuition for the first theorem. Are there any questions about the first theorem? So let me present.
Sorry, I have one.
Yes.
So maybe it's a stupid one. But you say that the perturbations keep increasing, right? But you said that because epsilon I is small, then you can ignore the second order terms. But if they keep increasing, won't these terms become relevant at some point?
Yes, they might. So the thing that I show now is that equilibrium B is not asymptotically stable.
Right.
Similarly, equilibrium A is not asymptotically stable. So now we know both of them are not asymptotically stable. We show in the paper that you always converge from any initial state, you must converge to an asymptotically stable equilibrium from almost any. And therefore, if you must converge to something and it's not a pure equilibrium, it's something interior with miscoordination. Okay, so now let me briefly present the other two results. The second showing that the stability of miscoordination can only happen if there is heterogeneity. If everyone has the same sample size, it never happens. So specifically, this is the second theorem. Assume that in both populations, everyone has the same sample size. So some K1 in population 1, some K2 in population 2. Then there is at most one interior stationary state, and it's unstable. So perhaps the situation is either in the left-hand side, it's a game in which equilibrium A is risk dominant. In this case, there will be no interior states, and from any initial state, we will converge to the risk dominant equilibrium. This is a situation similar to what is characterized in Oyama et al. Paper from 2015. And in this game, it's like a hawk-dove game that each population has a different risk-dominant action. And in this case, if everyone has the same sample size, and in this example, everyone has sample size 3, then depending on the initial, then we have a single interior state, and it is unstable. And therefore, from almost any initial state, we will convert either to this equilibrium or to the other pure equilibrium. So if there are no questions about the statement, let me present a brief intuition. So the first thing to observe is that this function of Wi of Pj, the probability of new agents in population I playing action A, is strictly increasing. It is strictly increasing in the share of agents in the other population that play A, and that Wi of 0 is 0 and Wi of 1 is 1. The next observation is that because Wi is a polynomial and it is strictly increasing, then its inverse is well defined, it is smooth, and also has the properties that 0 and 1 are fixed points also of the inverse function. The next observation is that a state is stationary if and only if the two curves intersect. If the two curves intersect, it means that exactly if we start in P, we always remain in P, because the share of new agents that will play action A will be the same as the share of the old agents who play action A. So this will only happen if P1 is a fixed point of the of W1 of W2 of P1. The next observation is that the curves can only intersect in a finite number of points, because W1 of W2 of P1 is a polynomial. And the next one is that, so they only intersect a finite number of times. Each time they intersect, it is stationary state. And the next observation is that stability changes from one neighbor to another. It's like one is asymptotically stable, another unstable, asymptotically stable, unstable. This property holds generically. There might be some non-generic situation that would violate it. So in the paper, we give a bit slightly more accurate condition that also hold for the non-generic cases. And the final observations about these curves is that a stationary state is asymptotically stable if we have two characterizations for them. The first is that the slopes, so the derivative of W1 of P2 is the slope of the learning dynamics. If the product of the slope of the learning dynamics is sufficiently small, if the product is less than 1, then it is asymptotically stable. The slope of the learning dynamics tells you how strongly the new agents react to a small perturbation in the share of agents playing action A in the other population. If the slope is small, it means that if now the share of the other population that play A changes by epsilon, the change for the behavior of the new agents will be less than epsilon if the slope is less than 1. And this tells you that the product of the slope is what determines whether it is asymptotically stable or not. In terms of the Jacobian, this will determine whether the eigenvalue is the largest eigenvalue, the value of the largest eigenvalue. Or in terms of the phase plot, this will be, you can see this in the phase plots in whether WT is below or above W1 to the left of P. So let's see here, for example, this is an unstable here. W1 is above W2. This would imply that the product of the slopes, the slope of W2 is the slope that you see here. The slope of W1 is the inverse of what you show here. So you see here W1 as a function of P2. So it will be like the slope when I change it by 90 degrees, when I look at P2 as the x-axis. So in this case, the product of the slope is larger than 1. The W1 is above WT left to the point, and therefore it's an unstable state. So the only thing that always the stability change from stable, unstable, stable, it always changes each time. And it only depends which curve is above which and whether the slopes are, the product of the slope are less or more than 1. So these properties of the curves allow me to prove the second theorem. And let me show you it unless there are any questions about these properties. Okay, so we prove it by deriving an interesting property of binomial distribution. Let's define Fkm of P as the probability that a binomial random variable with k trials and probability of succeed P is at least M. The probability that I will have at least M successes when I have k trials and probability of succeeding P in each trial. And observe that this f of k is a function of P, the probability of succeed. It always has fixed point at 0 and 1. If the probability of succeed is 0, I will never succeed more than M times. I assume that M is at least 1. If the probability of succeed is 1, I will always succeed at least M times. I assume that M is between 1 and k. And F is strictly increasing. There is an existing result in the mathematical literature of Green from 83, showing that this CDFF is at most one interior fixed point. What we needed for our paper was a slightly stronger result. We needed that the composition of 2F, we needed to have at most one interior fixed point. This is what we prove in the paper. We adapt the proof technique in Green to show that not only F, but the composition of two such F is one interior, is at most one interior fixed point. And the proof idea is showing that it has the decomposition has at most one inflection point. This implies that in our setup that the slope of WI is unimodal. if all agents have the same sample size, the slope is unimodal, the slope is larger in interior points than in the corner points in the pure equilibria, and this would imply that there is strong reactions to perturbation. If you are an interior state, the slope of R large, the population reacts strongly to perturbations, and therefore it will be unstable. And we show that having at most one interior fixed point is equivalent to the W1 of W2 to have at most one rest point, and this would be equivalent to any environment with homogeneous sample sizing having at most one interior stationary state. The proof of theorem 1 showing that if no one has sample size 1, so we assume that everyone has the same sample and it is larger than 1, and the proof of theorem 1 shows that if no one has sample size 1, then the pure equilibrium, then at least one of the pure equilibria is stable, and therefore we know that the interior stationary state must be unstable because it's a neighbor of one of the pure equilibria which is stable. Are there any questions about the sketch of proof? So the third result showing that there are many heterogeneous populations that have locally stable miscoordination as long as U1 and U2 are sufficiently far from 1. So what we show is that one can always add agents with large samples to populations with relatively small sample to obtain an environment that admit locally stable miscoordination. The formal statement, let's say for the case in which both UI are in the same direction. So this will be if UI is larger than KI, then we can always, there is always some number between 0 and 1, alpha I, such that if we look at the population in which alpha I of the population have sample size Ki, it's a finite sample, and the remaining 1 minus alpha I have this very large sample size, then it always admits an asymptotically stable interior state. And we have also in the paper a similar formulation to the case in which the UI in the different sides of 1. Let's perhaps look at it in an example. So in this example, U1 is equal to U2 is equal to 2.5. If both layers coordinate on A, they each get 2.5. And we look at a situation in which 40% of the agent have sample size 3 and 60% have sample size 1,000, very large sample size. In this case, the risk dominant equilibrium for both populations is action A. So this action A is locally stable. If we start from both populations play A with sufficiently large frequency, we will converge to everyone play A. But if we start in a state in which most of the agents play B, only few of the agents play A, then we converge to this interior equilibrium in which about 20% of the population play A and 80% play B, and this is robust to small perturbation. Any small perturbation that takes us a little bit away, the population would converge back to the interior state. And observe that this interior state is not a Nash equilibrium. When players are here, the players with the large sample almost always play the unique best reply to the distribution, to the true distribution of player of action. But those with small samples, substantially part of them, they play the best reply to the sample, but this is not the best reply to the true distribution of the population, and therefore they make mistakes. In this example, those with small samples get a somewhat lower payoff of 0.76 instead of getting 0.82, which is what they could get if they would play the true best reply. So the proof idea is that in heterogeneous populations, some agents have small samples, others have very large samples. Generically, the interior state is not a Nash equilibrium. Those with large samples know what is the true best reply to the opponent distribution. They always play the true best reply to the opponent distribution, and their play is completely independent of any small perturbations. Any small perturbation doesn't change the unique, strict best reply to the opponent distribution, and therefore those with large samples do not change their play after a small perturbation, and therefore this decreases the overall sensitivity to small perturbation. Those with small sample size do react to our to small perturbations, but if the smaller their share, the smaller the sensitivity, and this allows in some situations, specifically if the UI are sufficiently far for one, for the overall sensitivity to be sufficiently small such that the interior state is asymptotically stable. Are there any questions about this last theorem? So let me use the brief time I have to discuss a couple of things. The first is empirical relevance. So whether our results are only an abstract mathematical exercise or is there some empirical relevance? So to show some empirical relevance, I need to find some real-life scenario in which it has three conditions. There is heterogeneity in the sample sizes. We either directly observe it or at least it's plausible that some agents have small samples and others have large samples. We need to show that there is an interior state with miscoordination that persists, and we need that this interior state will not be a Nash equilibrium. That is, that a substantial share of agents will behave in a way that does not seem consistent with maximizing their payoff. So I need to find an example with these three properties. So the application we have in mind is bargaining either in housing market or used car markets. And the bargaining is something like the hawk-dove example that I presented originally, that there are two coordinated outcomes, coordination on high price, which is good for the seller, like hawkish seller and dovish buyer, or coordination on low price, but there are also interior states with miscoordination. So the first thing is that I claim that the heterogeneity of sample size seems plausible in this setup. Let's focus on the housing market. Some players are real estate investors. They have large samples, lot of experience, and probably they know quite well the distribution of behavior in the other population. But other agents are inexperienced players who buy or sell a house for the first time in their life. And it seems plausible that first, perhaps they don't fully, they rely on anecdotal evidence, perhaps on how some friends of them and family behave when they sold a boat or house. Perhaps they consult with the real estate agent, but perhaps they don't fully account for what he gives them, as he has different incentives than them, and therefore perhaps they don't fully believe to what he says. And they perhaps give a lot of weight to what the friends and family told them, whether it's good to be hawkish or dovish, let's say when you set your list price when you sell a house. And we know that there is a common bias of law of small numbers, that people seem to think that small samples are representative of large population. And Koster and Roendahl in a recent paper, they empirically study a Dutch housing market. They saw that
sorry, can I just ask a clarification? So
yes, please do.
Is the idea that there are two populations? One population is the agent, and the other is the agent's population, and the other real estate agents, and the other one is the consumer population, and they have there is heterogeneity across these populations in terms of K, but not within, perhaps.
So no, this is not what I have in mind. This wouldn't sufficient for our result. What I have in mind that in both population, both sellers and buyers, and some agents are more naive with small sample. Some agents sell the house for the first time in their life. They only rely on anecdotal evidence. Some buyers buy the house for the first time, while other sellers and buyers have either a lot of experience or perhaps they fully follow the advices of an experienced real estate agent. So I think in each population, I need a heterogeneity of K. I need both sellers and buyers, some of them to be sophisticated with large samples and others less sophisticated with small samples. So they show that there is substantial heterogeneity in the list prices of similar houses that they claim to be similar according to the econometric observable in location and quality have quite substantial heterogeneity. Those that requiring a low list price have a clear advantage that the house is sold faster on average, but on a lower price. They claim that the heterogeneity on the list prices can be explained by maximizing payoff, but this requires a very high annual discount factor. The differences in the time that you sell the house in their sample of 20 years in the Dutch housing market is that if you set a substantially high list price, it on average allows you to sell the house later, but only a bit later, only a few months later. So this can be consistent with maximizing payoff only with a high discount, annual discount factor of 25 to 30%. Our paper, and this might be consistent with our model that some players, perhaps they don't have such a high annual discount factor, but because of relying on small sample, they think by mistake that setting a too high list price will postpone selling the house for many years, and therefore they make the mistake of setting too low price. In a somewhat older paper of Genesove and Meyer, they show that in this paper, they don't know which of the sellers is owner-occupant and which is an investor. Here they have they study US data and they know which sellers are owner-occupants and which are investors. And they show that they have substantially different distribution of list prices. So indeed, sophisticated players and those inexperienced seem to behave differently in this setup, which is consistent with our model. And some results of Larsen studies efficiency in bargaining over used cars, and it shows that bargaining often fails, about a third of the cases, and that there is substantial inefficiency, and that it seems that only a small part of the inefficiency is due to incomplete information. Typically, the main explanation why we don't get efficient results in a bargaining situation is due to incomplete information, but it shows that it's only a small part of it, and this is again consistent with our predictions. Another thing we want to show numerically that our qualitative result that stability of miscoordination happens with heterogeneity in the noise level also holds with other specifications. So we analytically study only this specification of action sampling, but numerically we look at the popular logic dynamics that each agent has some noise level. And we show that if everyone has the same noise level, then we can get interior stable state, but we can only get it with we have very high level of noise. If players do a lot of mistakes, like 27% of the time playing A, when you face an opponent population that always play B. So very high probability of doing a clear mistake. On the other hand, if we introduce a variant of logic dynamics with heterogeneity of the noise level in each population, this can induce stable miscoordination with smaller, significantly smaller level of noise, and the kind of phase plot that you get seems quite similar to what we get by action sampling. So this is like and similar preliminary numeric results suggest that also in other dynamics, the best experience payoff sampling dynamics and dynamics induced by representative sampling, again, if you introduce heterogeneity in the noise levels, again, miscoordination can be stable. So, for example, here, on the same parameters of U1 equal U2 to 2.5 that I showed in theorem 3 before, if everyone, I require them to have the same level of noise, I need very high level of noise, eta equal 1, to get some stable interior state, but this is, players do a lot of mistakes in this. While if I allow heterogeneity, I can have a population in which about half of the agents have moderate level of noise, and half of them have no noise at all, almost no noise at all. We get phase plot very similar to the one that we get with action sampling, with a stable interior state in which few agents play A, most agents play B, and we are with miscoordination. The final thing is we have a clear testable prediction that miscoordination would persist if we have heterogeneous sample size and the UI are not too close to 1, and we encourage people to test it experimentally. Existing this has not been tested before. Existing experimental paper does suggest that action sampling is plausible, that the aggregate behavior of agents can be explained relatively well by action sampling, better than predictions of a quantum response equilibrium or Nash equilibrium. and that when players are randomly matched, and each round they can only observe the behavior of their own opponent, they seem that the behavior is consistent with something like action sampling, with sample something between 3 and 12. Like each player remembers and gives some weight to the behavior of its own opponent in the previous rounds. In some situations, player seems to try to teach. If there are two equilibria, one of them is payoff dominant, some agents do not behave like best replying to their sample. They seem to try to teach the entire populations of the matching group to go to the Pareto better equilibrium. But what we think that if we will choose a game in which neither equilibrium is payoff dominant, so one of the equilibrium is better for player 1, another for player 2, then we think that we can get the stable miscoordination. If we want to have heterogeneity in the sample size, then possibly this will require to give better feedback about the behavior of other players to some players and worse feedback to other players to get the heterogeneity that we need for our result. So if I conclude, coordination game admits two types of equilibria, pure equilibria and misequilibrium with miscoordination. Many results in the existing literature showing global convergence to the pure equilibria, but we show the opposite result, that sampling dynamics can induce stable miscoordination if some agents base their choices on noisy anecdotal evidence while others rely on large sample, and if in each population one of the action is sufficiently risk dominant. So in our parameterization, if the UI are not too close to 1. The analytic result is only for this specific best reply sampling dynamics, but numeric analysis suggests that the same insight holds for many learning dynamics, and the predictions are empirically relevant and can be tested in the lab. That's it. Thank you.
Thank you very much. I will now turn off the recording and